Okay, good morning everyone. Good morning. So I'm going to continue from last time. By the way, is the volume too high for everybody? Is everybody okay? Okay, alright. So what I'm going to do is, from last time, I'm going to draw the 2D circle view of the cross section, label all the forces that we came up with, the moments that we came up with, and then revisit some of the things that we looked at, and then start writing out the stress matrix and draw the state of stress on a volume element. Okay? And then I will also continue to do this for another problem. We may not end up solving that completely today. Take it up on Friday, the remainder of that. By Friday, I'm going to start looking at principal stresses. Okay? And I just want to reduce the volume just a little bit. Okay, I think this is better. So here is a 3D view of the problem from last time. Not 3D, 2D view. Okay. We had the y-axis going up, the z-axis was pointing to my left centroid. Z-axis, then I have the x-axis coming out of the page. Just for fun, just to spice things up, I'm going to say that besides the forces and moments that we saw last time, I'm going to have a normal force directed into the cross section. Okay, this is just an addition from last time. I'm going to say there is a normal force Nx. From our calculations last time there weren't any, but I'm just throwing one into the mix, just to make things a little better. Okay, this is equal to a magnitude of, let's say, I think I had this as around 200 newtons. Then I had the following forces and bending moments. There was a torque Tx which was counterclockwise. Newton meters. Then I had the shear forces along the z and the y axis, so Vz was 300 newtons. And then I had Vy, which is pointing along the positive y, 200. Then I had the bending moment about the y-axis and the z-axis, about the negative y-axis and the positive z-axis. This bending moment was mz, which was I think 200 Newton meters. And then I had an my, which was around the negative y-axis. Newton meters. Then I had our points of interest, point A, B, and C, C being the centroid. Point B. And we were told the radius of this cross section was 10 millimeters. So R 10 mm, okay. And polar moment of inertia about the y and the z axis, these are all given to us. Yes, sir.
So in the last problem we did, point B was on the right. Does it make a difference?
The point B was on the right?
Yeah.
Okay, let's just say there is another point. Okay, let's do it for all these points. Alright. What I want to do is I want to write the state of stress for all these points. Then I want to draw the volume element and I want to see how one informs the other. Which implies that I need to calculate the stresses at all these points. We did the following last time. At the point A, I was able to calculate the shear stresses due to the torque as well as due to the shear forces. Okay, so tau A due to the torque Tx. This was Tx. C by J, Tx was 200. C is the radius. We did this calculation last time, so and J is pi by 2. Ten by 1000 to the power 4, r to the power 4. We were able to write the subscript for the shear stress. The second subscript is always the direction of the area normal, which is coming out of the page in this case, which is the x-axis. The first subscript is the direction of the shear stress itself. At the point A, due to Tx, the shear stress is going to be pointing to the left. Okay, so this is going to be Zx. The thing that I wanted to point out last time was that even if when I write it as Zx, it does not necessarily tell me, just writing this out does not tell me what the direction of the shear stress is. Is it to the left or is it to the right? Okay, that is going to come from the drawing of the volume element. Alright, so if you do the computations, this ended up being 127 megapascals approximately. 127.3 megapascals. Then we said, okay, shear stress at the point A due to the shear forces. What are those? I'm going to write them out. Tau A, Vy, tau A due to Vz. Okay, two of them. For the shear force Vy, if I look at the calculation, so if you want to write out the formula, this is Vy, Q, I about the neutral axis. We said that if I have a shear force in one direction, the direction of the neutral axis is perpendicular to the shear force. So this is going to be in the z direction. T times tau. This is the generic formula for transverse shear stress. Value of Q in this case is y bar prime times A prime. A prime being either all the area above the point A or below the point A. Okay? So A prime is above or below A in this particular case. And it is quite obvious that if I look at the area above the point A, there is no area above the point A. Okay, so which means that Q is 0 for me. And so tau A comma Vy is actually 0. Does this make sense to everybody? Person in the back, do you have a question?
I'm just trying to, that arrow on M sub Z, on the left, which direction is that?
This is pointing this way.
Yep. Is that clockwise or counterclockwise? Okay.
Counterclockwise with respect to a person sitting and looking at the z-axis from the left side.
Okay, thank you.
Okay. Am I making sense to everybody? Yes, yes.
So if you took the area below for Q, then what would make it 0?
Fantastic question. Right, so let's say that this is the point A. Here is the shear force, Vy. Now, according to the definition of Q, this is my A prime. So Q is A prime times Y bar prime. What is the definition of Y bar prime? It is the distance from the centroid of the cross section or the neutral axis, distance from any point on the neutral axis to the centroid of the shaded area. What is that value? has to be 0. Right? So in that case, my y bar prime is 0. So whether I take the area below or above, doesn't matter. So it is easier to think of the area above because there is no area above. Does this make sense to everybody? Once again, what is the definition of y bar prime? Y bar prime is the distance from the neutral axis to the centroid of the shaded area. To the centroid of A prime. This is 0 in this particular case because the centroid of the area A prime and the neutral axis are coincident. There is no distance between the two. Okay, so in this case also it will end up being 0. Alright. Then tau A V suffix Z, Vz, Q. Now for the shear force Vz, the neutral axis becomes the axis perpendicular to that on the plane of the cross section, please, not the axis coming out of the page, because the shear force is acting on the plane of the cross section. So all the shear stresses will be on the plane of the cross section. This is going to be Iy. T tau. We went through these calculations last time. I'm not going to do these out. But the direction is Zx once again. Z is the direction of the shear force, Vz. X is the direction of the area normal to the cross section of the plane that you're interested in. After we did the calculation, this was 1.27 megapascals, but this was pointing to the right because this has to track the direction of the shear force. This was pointing to the left. This was pointing to the right. So if you want, you can draw a figure here saying tau A due to EZ. Okay? They are at loggerheads with each other, which means that we have to subtract one from the other, depending on whatever you want to call as a positive or the negative, but I don't like saying positive and negative, so we write it out this way. So tau A, generic tau A now, suffix Zx, because all of them, the shear stresses at point A are in the Zx sense. Okay, so this is going to be tau A dx minus tau A Vz, both of them having the same subscript, and 127.3 minus 1.27, so this ends up giving me approximately 126 megapascals pointing to the left. Okay. Any questions so far? Yes.
If the tau A dy had been a value, would we include that in the tau A total equation?
Absolutely, absolutely. So we are going to see that happen for this point C, which is the centroid. It's going to have a contribution due to both this guy and that guy. Okay, so we're going to see that. Once again, are there any questions before I proceed next? This is where I think we stopped last time. Now I hope it is clear why this guy is 0 for everybody, right? Okay, whether it is above or below, it is easier to think of something above because there is nothing there, so it is 0. Okay. All right, then I look at the contribution of the bending stresses and so on at the point A. Okay, so shear stresses are done, so I want to find out sigma at A. What are the contributions? Just for simplicity, I'm just going to draw the cross section with only the contributors to the bending stress or the normal stresses at the point A. Okay? You don't need to draw this if you don't know. We are done with the shear forces, we are done with the torque, they cause only a shear stress. So I'm looking at the remains of what is left. I'm interested in the point A. If you have a normal force, it's either pushing into the cross section or pulling away from the cross section. So in that case, this normal force here, Nx, is going to cause an average normal stress, which is compressive. And this is going to be the same at all points on the cross section. Okay, so I'm going to have sigma A due to Nx. This is just minus Nx by A, or if you don't like the negative sign, just write it as compressive. Nx was 200, area is the area of the cross section. Actually pi times 10 by 1000 because the radius is given to me. Okay, so sigma A Nx, the value is the following, it's around 0.95 megapascals. Compressive. It is very important to write that this is compressive. Okay. What are the indices? If you know the second index for the bend normal stress, then the first index is the same. So this is going to be x, and it is quite easy to see that the normal force is in the x direction, so the stress direction is also going to be in the x direction. Does this make sense to everybody? Second index is the area normal. If you're looking at normal stresses, both the indices have to be the same. And if you're in doubt, you can always look at the direction of the normal force. It is pushing into the page or away from the page, which is the x-axis. Then I look at the contribution of the remaining two creatures, sigma A and y, sigma A due to mg. This is the y-axis, x-axis, and the z-axis. Point A, if I look at the bending moment my, for the bending moment, the point is on the bending axis itself, which means that there will be no stresses at the point A due to this bending moment my. Makes sense to everybody, right? This is something that we have been speaking about quite a while. If you have a point on the bending axis, which is a neutral axis for this bending moment, then I don't have any bending stresses at that point. Okay? So this is automatically 0, because point A is on the axis of bending. Sigma A due to mz, I make use of the formula, okay? Because I know that first of all point A is not a point on the z-axis, so there is going to be some bending stresses. So this is mz times some distance by I. So watch this carefully. You will notice that I have not used the negative sign. When we derived the bending stress values, we said that it's minus my by I something, right? I am not using the negative sign because we are going to look at what the state of this bending stress is by seeing how the cross section is twisted, not twisted, how the cross section is bent by the bending. Okay? So mz, the way it acts is that it is going to take all the fibers below it to be pulled out of the page, all the fibers above it to be pushed into the page. Does this make sense to everybody? Okay, so in some sense, it is the same example that we have been looking at for a while. So the bending moment axis is to the right, so that if I take this as the plane of the cross section, I am doing the following. So all the fibers to the top are pushed inside, all the fibers at the bottom are pulled out, and this keeps reducing in intensity as I reach the neutral axis. The neutral axis for this bending moment is the z-axis. Any point on the neutral axis will not see a bending stress. So at the point A, the state of stress is going to be compressive. Questions? Does this make sense to everybody? then I just do the calculation. So I don't put the negative sign. You see, we visually inspect and see, okay, are these stresses going to be tensile or compressive? Okay, once again, looking at the way the bending moment is acting, if I use the fingers of my right hand, my thumb is pointed along the z-axis, the bending moment is such that it's pushing the top of my thumb into the page or into the plane of the chalkboard. And so all the fibers which are on the top half will be in a state of compression. All the fibers in the bottom will get pulled down. Point A is unfortunately a point on the top half, so it's in compression. So sigma A due to mz, write the indices. Area normal is x, so automatically the bending stress is also going to be in the x direction, and so this is going to be mz, which was 200 Newton meters. Y is the distance of point A from the neutral axis. For the bending moment mz, the z-axis is the neutral axis. Okay, so y is the distance of point A from the neutral axis. So this is half the radius, half the diameter or the radius itself. Right, so this is the distance of A from neutral axis for mz. Divided by the area moment of inertia, pi by 4. Area moment of inertia is not the same as the polar moment of inertia, but for a symmetric cross sections, the area moment of inertia about the planar axes y and z will add up to give you the polar moment of inertia about the x axis. Okay, crunch these numbers. This is compressive. So sigma A mz xx is the following: 255 megapascals approximately. Compressive. So the net normal stress, because of the fact that the normal stress due to the normal force is compressive, because of the fact that the normal stress, the bending stress, which is a normal stress due to the bending moment, is compressive, it is an additive effect at the point A, the totality pushing it further into the page. So sigma A xx is sigma A z plus sigma A and x, because they are both compressive. (255 plus 0.95, so 256 megapascals approximately. So 256 compressive. I'm going to push this board up. Okay. Yes, question.
So I just wanted to make sure. So for the when we're getting sigma A mz, you said that the mz was positive because it was compressive and it was normally negative, so it's negative, negative is positive. Is that why?
Yes.
Okay.
That's one way of thinking about it, but it is kind of hard to keep carrying through the negative sign every time. So the idea is you visually recognize, okay, what is the effect of this bending moment? By saying it is pushing fibers into the page here and pulling it out of the page. And so it's going to be a compressive.
You just say
Because there is reason to write it as, okay, mz times y by I, negative negative becomes positive. So one will write it as a positive value, which will end up being counter to the fact that this is also a compressive.
okay.
So then one will end up doing 256, 255 minus 0.9.
Okay.
Yes.
For the bending stress of A with respect to my, is the neutral axis still the z-axis, or does it?
No, the
It's
neutral
the
axis.
y-axis?
Yeah, for my, the neutral axis is y axis. If you want me to write it out, so. So the way to remember this, and I think we've discussed this before, if you're looking at shear forces, the neutral axis is an axis perpendicular to the shear force and on the plane of the cross. If you're looking at bending stresses, the neutral axis is the same as the bending axis. Okay, in this case either the z or the y-axis, depending on which bending stress you're looking at. So perhaps I want to write this again, okay, just so that we are all very clear. The neutral axis. For bending stress calculations. And the neutral axis is axis perpendicular to the shear force. My symbol for perpendicular, once again, for shear stress. Shear stress calculation, and when I say the neutral axis is perpendicular to the shear force, it's on the plane of the cross section. Okay. So now we need to draw the volume element, okay, draw the state of stress on the volume element, and then write out the stress matrix. We got to do this for other points as well. So I'm going to take, after I do this, I'm going to take the point C, which is a more interesting point. It's a centroid. So let me complete the point A. Okay, so once again, you don't need to redraw any of these things. I'm just drawing it out to see how these are depicted clearly. So volume element. And stress matrix. Cross section. Point A. I have an axis system. Y-axis and Z-axis pointing to the left. Okay. At point A, the direction of the shear stress is going to be pointing to the left. We just decided that was the case, right? The last panel on the top there. So draw a volume area element. So draw an area element, just a rectangular box. First draw the direction of the shear stress, which is going to be pointing to the left. This is tau AZX. Then the direction of the bending stress is pushing into the page, right? It's going to be along the x-axis, but it's compressive, so it is pushing into the page. Kind of hard to draw that out, but I hope this makes sense. It is pushing into the page, and this is sigma A XX. Take that area element out and draw it out as a volume element. So take it out. Okay, so here is my volume element. On the face that I see, which is the face that is closest to me, I start drawing out whatever are the stresses that I see on this area element. But before I do that, I set up my axis system. Okay, before I do that, vertical axis is the y-axis. Okay, the axis that is slanted out. Okay, so I'm essentially taking this guy and then spinning it towards you. So if you want, you could have drawn the y-axis and the z-axis here. So which means that if I'm looking at this particular face, the y-axis is vertical, the z-axis is pointing to my left. Okay? So this is going to be my z-axis, and my x-axis is coming out of the page. Okay? Then I draw these stresses themselves. First of all, the shear stress. So that's the first arrow. Then I see, okay, it has to be balanced, so I have to have an equal and opposite stress on the back face. Then I'm going to have two more on the sides, because this is causing a couple moment. One on this side and the other on the opposite side. This is the effect of the shear stress, but on the same volume element, because of the fact that you have a combined state of loading, there is also going to be impressing upon itself the normal stress sigma AXX. So on the face that you see, I'm going to have a normal stress pushing into the face. This is sigma AXX. This was, of course, A, ZX, and so on. Which means on the opposite face, I need to have something equal and opposite to sigma AXX. So does this make sense to everybody? And this is the phase that I'm viewing here. Does this make sense to everybody? So you have to draw all of them on the same volume element. Okay, you cannot draw them on two different volume elements because this is a combined state of loading. If you have done this for the quiz, that is completely fine because you did not see this until today. But from now on, if you have a combined state of loading, it has to be drawn on the same volume element. It is showing you that, okay, this fellow here, this fellow A sitting here, he is being suffocated by all these different stresses. Okay? And if you want, you can write out these arrows as tau A x to z. It is completely unnecessary because last time we decided that the magnitude of this guy is the same as the magnitude of that guy, so there is no need to switch the indices. Okay, so if you have a shear stress, tau ij is the same as tau ji, where I can be x, y, and z. J can be x, y, and z, and I is not equal to j. That is, I choose I to be x, j could be anything other than x. If I say xy, then it is the same as tau yx. If I say tau zx, then it is the same as tau xz. They are symmetric. Okay, so shear stresses are symmetric. And you see that these are physical ideas, right, where the stress is symmetric. And we take these physical ideas, and because you have to do these in a computational standpoint, we write matrices. What's the use of writing a matrix? A matrix is nothing but a mathematical tool. It does not have a physical significance. You provide the physical significance to it. But a matrix is very simple and nice for mathematical computations. You feed entry data into a computer using matrices, using vectors. It is more efficient to store data that way. So which is why you write things in a matrix. So we say sigma A. Here is the standard form of writing the stress matrix. The diagonal elements are all the normal stress elements. So this is going to be sigma A XX, sigma A YY, sigma A ZZ. The off-diagonal elements are all completely symmetric, so it is sufficient if you write only the first set. So this is tau A XY XZ tau A YZ. Everything else is just going to be symmetric. So this is also tau A XY. This is tau A XZ. Tau A YZ. Okay, they are all symmetric elements. So this is the same as that. This is the same as that, as you can see. And these two are the same. So this is a symmetric matrix. Sometimes it will so happen that there will be no shear stresses, you will have only a diagonal which will be composed of the bending stresses or the normal stresses, that becomes a diagonal matrix. Computations are much more simpler that way. Storing of information is much more efficient that way. And if I sneak in and write out for us, I don't have any sigma A in the YY and the ZZ, so they cancel off. So for us, excuse me, sigma AXX is, there is a value 256 megapascals. 0, 0, the other two diagonal elements are 0 because there are no bending stresses there. Then the off diagonal element, tau AXY is 0. There is no XY shear stress, so this guy is also 0. Can everybody see as I'm writing here? People in the back and the sides. Then I'm looking at tau AXZ, which is a value that we calculated, which was 126 megapascals. 126. 126. I don't have a tau AYZ, so tau AYZ and ZY, they're both equal to 0, so those two off diagonal elements are 0. Okay? Are there any questions on what I have written here? Yes?
Two questions. So when you say draw the matrix or the stress of a matrix, I forgot the terminology, is it always going to be where you both combine the bending stresses and the shear stresses in the same matrix? So at any point you only have one stress matrix?
Right, so 1 point. So first of all, not just bending stresses, this is inclusive of average normal stress as well. So this is in totality called as a normal stress because it includes bending stress,
Yeah.
and it also includes the stress due to the normal force.
Exactly. Like yeah.
Right,
the
so the
normal stress.
combined
Yeah.
effect of that.
Yeah.
This is the combined effect of torsion and shear, right? And if you look at it, each point is actually a volume element in reality. We are just saying that the volume element, we are drawing it as a volume element so that it's much more visible to us. But really, there are all these stresses that are sitting in a volume element at a point. And you've got to do this for each and every point.
Yeah. Sure.
So for different points, these stresses will be different. And what you'll find out is, okay, we're not going to do this in this class, okay? But you can find the eigenvalues of this matrix. You can write the same set of matrices for different other points, point B, point C, point D, find the eigenvalues of those matrices. Whichever gives you the largest value of the stresses is the culprit. That's where your failure is going to start. Okay? That all belongs to what is called a static failure theory. If you're taking machine elements, you'll come to know about it. Okay? So we will not be doing that in this class. Alright, so that's done for point A. I want to look at point C. More interesting. I'm going to push this board up. Okay. Alright. So just to do it for point C, I'm going to redraw the cross section. Once again, you don't need to do it. Okay, Y and Z. Point C is my point of interest. I have the following forces, torque and normal forces acting on it. So once again, normal force in X. Okay, then I have BZ and BY. Bending moments, MY and MZ. And then the torque, Tx. Now let's start whittling it down one by one. Okay, and I'm going to do these calculations a little fast, just the calculations, not the part of writing the stresses out. Let's start with the shear torque Tx. So tau C. What's the shear stress at point C due to the torque? It has to be 0, right? Because the shear stresses due to a torque is going to start from 0 at the center of the cross section and increase all the way to a maximum at the outermost circumference. Okay, so we've seen this before, so this is 0, end of the story. Then I'm going to have shear stress due to the next one. Now is this 0?